Welcome everybody to our klogW talk for today. We have Denis Bartolo speaking to us. Denis is the second of three speakers in this series, in this mini series, which is honoring the newest GSNP fellows, APS-GSNP fellows. So we first had Jean Carlson, who spoke in November, and you can access her talk if you missed it on our website, which is given here. Today we have Denis, and Daphne will introduce Denis. And in Feb, we have Yamir Moreno from the University of Saragossa, who will speak on February 22nd. Just a few words before we get started. So we are the topical group of statistical and nonlinear physics of the APS, and we welcome you to join this group if you aren't already a member. You can join it by going to this website, engage.aps.org. Just search for GSNP, and so you'll enjoy all the benefits, including in the upcoming March meeting. There are focus sessions that are organized by GSNP, and there are both graduate student and postdoc award sessions as part of GSNP.
Painted Sabo visiting both of their graves next to each other. I don't know why, but
Will the person who's speaking just unmute themselves? I mean, mute themselves, not unmute.
Done.
Yeah, thank you. So when you go to, if you want to become a member of GSNP, when you go to the Engage website, and click and search for GSNP, you'll see a landing page that looks like this. And this allows you to see all the things that are happening, join in community discussions, and see upcoming events. Finally, I want to just say a couple of words, and here is the link to join GSNP. A couple of words about Zoom etiquette. So the way this works is during the talk, we would like you to put yourself on mute, but you're welcome to pose questions in the chat rather than unmute yourself and ask. This will make it easier for the speaker to keep going. If there are questions of a clarificatory nature, one of the hosts, that includes Daphne, John Beckhofer, and myself, will unmute ourselves and ask Denis directly. But otherwise, if they're more general questions, we'll save them to the end. After the talk, you're welcome to ask questions yourself, or if you don't wish to do so, you can still put them in the chat. So with that, we will stop, and I'll pass it on to Daphne to introduce our speaker.
Hi, welcome everyone. Right, it's our great pleasure today to have Denis Bartolo as our speaker. And it's really wonderful to see so many people actually on our first 2022 klogW. I hope it stays like that. Oh, and I hope that you all join APS and in particular GSNP, like Shubha was talking about. Okay, so Denis is a professor of physics at ENS in Lyon in France. He studied experimental physics and chemistry and completed his PhD in theoretical physics at the SPCI in Paris. He did postdoctoral research at ENS in Paris and joined as an assistant professor in 2006. And then moved to Lyon in ENS as faculty and full professor in 2012. As he describes, he likes combining experiments and theory to investigate all this awesome active matter, soft condensed matter phenomena that he's going to talk about today. So with this, I'm going to pass this on to Denis. Thank you for joining us, and hopefully all of us in this Zoom room can meet in some conference sometime soon. So.
Okay, thank you, Daphne. Thanks a lot. Thanks a lot for giving me the chance to present our work today. So I'm going to share my screen. Here we go. And okay, this should work now. Okay, so today what I would like to do is to I'm going to use a lot the F word because I would like to talk about flocking fluids. And more precisely, I would like to talk about their self-organization and the robustness of their emergent flows. So I guess that when you think about a flock, the first thing that comes into your mind is a flock of birds or any other group of animals all moving along the same direction, such as a fish pool, a herd of zebras and wildebeest. And I also like very much this last picture showing a group of pelicans all swimming as a flock on the Mississippi River. And what's really remarkable, at least to me, is that in these gigantic animal groups, such as in this huge school of jackfish, the fish do not have any communication tool to transmit information over a distance that would be comparable to the school size. And there is no leader to coordinate the motion of the entire school. There is no external bias that would constrain the fish to undergo this vertical motion. And yet, as a result of interaction between neighboring fish, this whole group managed to self-organize into this gigantic flock where all the individuals swim steadily along the same direction. And in fact, because of this, you might want to think about flocking as an emergent phenomenon, okay? A property that arises from interaction between microscopic constituents that would be robust at large scale. So if you want to think about flocking as an emergent phenomenon, you know that it should not depend too much on the microscopic details of the constituent, and this might invite you to think about synthetic realization of flocks. And that's what I would like to discuss today. So to be more specific, I would tell you a lot about this type of experiment today. So what you can see on this picture first is obviously a circular chamber. It is 3 centimeters wide. And this chamber encloses a monolayer of colloidal particles. So these colloidal particles are just polystyrene beads. Their diameter is 5 micrometers. And as it turns out, we found a way to motorize these beads. So it's nearly as simple as hitting a key on a keyboard. So that's what I'm just going to do right now. And on this real-time video, what you can see is that as the particles start propelling themselves, they interact. And as they interact, they self-assemble into this huge flock, gathering millions of colloidal particles. So you might want to think about it as a gigantic flock of colloidal robots or as a spontaneously flowing liquid. Okay, given the scale at which we have taken the video, we cannot distinguish the individual particle. We just see a fluid flowing in this circular chamber. And let me play it again. And what's truly remarkable is that after a very short transient, you can see that this initially random flow self-organizes into this nearly pristine vortex pattern. So this is obviously an example of an active material, and this is also obviously not the sole example of active matter that we know. I would say that over the past decade, virtually all the ingredients of soft matter have been motorized very successfully. I'm showing you here an example of active emulsions, of active liquid crystals, active colloids, and here active membranes. But in all these 4 early experiments, it's also very clear that the results of the interactions between the active units is a structure that is not really ordered at large scales. The dynamics looks very chaotic, and we do not see any clear large-scale structural order. And that's something that is very common in active matter. It's very clear from, sorry, what's going on? On this video that I'm sure you have already watched a million times. So that's a video from the Dodgix group showing the dynamics of an active nematic. And so this nematic liquid crystal is driven by molecular motors, and the result of this activity is the continuous folding of the nematic structure So we call it an active nematic, but when you think about it at large scale, this is actually an isotropic phase with a lively dynamics, but this thing is just isotropic as a result of activity which destroys structural order. So this destruction of structural order by activity can be illustrated on a different experiment. So let me show you this video that was taken by Ephraim Bililine in William Sievin's group in Chicago. So this is a colloidal crystal. The color indicates the direction of the crystalline axis. And in this case, the particles are not self-propelled, but their spinning motion is activated. And as the spinning motion is activated, crystalline order is suppressed at large scale. And you can see that this material turns into this very lively polycrystalline structure. So it really seems that activity very often destroys structural order and results in very chaotic flows. But this rule obviously finds a remarkable exception in the video that I've already shown you. In this video that I'm going to play again, you have a collection of millions of colloidal particles that can propel themselves. I'll tell you a little bit more about it later. But what is very clear that the result of this microscopic activity, on the contrary, is to structure the flow of the system into a steady, homogeneous, and very quiet structure. This is absolutely not specific to this very experiment. This type of polar matter or flocking matter has been realized using very different constituents. Andreas Bausch managed to make flocking fluids out of active filaments powered by molecular assays. In Steve Granik's group, they used a different type of active colloids. And I should also show you this early experiment by Olivier Dauchot and co-workers who used shaken grains. So this type of flocking motion that's stable at large scales is basically achieved over orders of magnitude in scale. And the question I would like to address today is twofold. So first, I would like to tell you how flocking fluids self-organizes their flow. And secondly, I would like to discuss the robustness of these emergent patterns. So first things first, I need to tell you how to engineer flocking matter. So the solution we found nearly 10 years ago is fairly simple. It consists in using a very old and well-known electrohydrodynamic instability that is called Quincke rotation. So I'm not going to spend a lot of time telling you about the motorization principle. I'm just going to flash the idea on one slide. It's not super important for what follows. So the idea is the following. When you apply a strong DC field to any insulating body immersed in a conducting fluid, the result of the electric field is to polarize the surface of the body. And the dipole orientation points in the direction opposite to the E field. In fact, if you increase the magnitude of the field, the situation becomes unstable. And the system jumps towards another configuration where the dipole makes a finite angle with the field. So if you remember electrostatics 101, if you have an E field and a dipole making a finite angle, you get an electric torque. And this torque actually powers the steady rotation of this bead. So I'm not expecting you to understand the subtleties of this phenomenon. The only thing that you could try to remember is that whenever you apply a strong E field to an insulating body immersed in a conducting fluid, you get spontaneous rotation. So this is the first trick. The second trick is even simpler. When you take a rotating body and you place it on a solid surface, it rolls. Okay, that's how wheels have been consistently working for millennia. It works very well, and that's how we make colloidal rollers. So let me give you a couple of orders of magnitude first. So the beads that we are using are 5 micron large. the gap between the electrodes is typically of the order of 20 microns, and the voltage you need to apply is about 1 or 2 volts per micrometers. So when the colloid concentration is small enough, you just have a gas of active particles all rolling along random directions. But when you increase the packing fraction, the system undergoes a so-called flocking transition. What does it mean? It means that, for instance, in this channel having the shape of a racetrack, all the particles spontaneously move along the same average direction. And that's what I would like to call a colloidal flock. Okay, an ensemble of active particles all moving along the same average direction in a very steady fashion. And to achieve this type of behavior, you actually need 2 ingredients. So first, you need self-propelled units. That's what we have with our colloidal rollers. And you need a second ingredient. And the second ingredient is that you need polar interaction between the particles. What you need is that, as a result of a collision, the particles should align, should be prone to align their velocities. So I'm not going to explain you why, but these colloidal rollers enjoy polar interactions, and that's why they form this form of flocking active matter. Good. So now, okay, we know that we have the 2 necessary ingredients. The question is, how can they self-organize their flows to achieve this very large-scale ordered structure? So I've been talking about flows, so I guess it's high time to show you a flow field. So this is an experimental flow field that we measured in a circular chamber. So at the initial time, all the colloids move along random directions. So the flow field, the orientation of the flow is just random. But very quickly, as I've already shown you, the system self-organizes, and you can actually see that some coherent flow structure emerges in this system. What is also very clear is that this flow is plagued by point singularities. And these point singularities are vortices and stagnation points. So that's the fluid mechanics terminology. In condensed matter, you might want to call them +1 and -1 topological charges for a vector field. So we have this flow that's plagued by topological defects, but in the course of the dynamics, the defects are annihilated by pair. And after a short transient that lasts a minute or so, as a result of the defect annihilation, we are left with this very smooth and a very neat azimuthal flow. Good. So the question was how do flocks self-organize their flows at all scales? And you can now rephrase it as how do polar active fluids heal their topological singularities? How come these topological defects can disappear? I've got a question, which is how persistent are what's the persistent length of the rollers? In our experiments, the persistent length is about 200 or 300 microns, which is very small compared to the system size. Okay, so to answer this question about the annihilation of the topological defects, what is really important to actually notice is that the point defects are not the only singularities of the flow. So what I'm showing you here is a heat map of the strain field, of the flow gradient. What you can see is that all the topological defects actually leave on a network, a fully connected network of domain walls. And these domain walls separate, there are like strong discontinuities in the flow field. They localize the strain and they separate regions with incompatible orientations. So if I now show you the density field in this active fluid, at the beginning of the experiment, you can see that we have density variations, but they are very long wavelength heterogeneities. They just depend on the way we inject the colloids in our microfluidic device. But as soon as we turn the polystyrene beads into active particles, what you can see that very typical patterns emerge. They give the impression of a folded structure, and I believe that this pattern looks like a bow tie. Okay, so I'm going to call them bow tie patterns. But I would like to stress that even though they look like folded structures, this structure is really two-dimensional, and these lines are actually strong discontinuity lines in the density field. So now we know that we have line singularities in these active fluids, domain walls in the orientation field, and bow ties in the density field, and they're actually two sides of the same coin. The edge of the bow tie is actually defined by the domain walls. So the question now is this, and the answer is the confinement. I've got a question which is about the confinement. That's a good question. The confinement is not needed. In fact, we need a container to do our experiments, but all what I'm going to show you today does not depend on the shape of the container. Okay, so I've got bow tie patterns, domain walls. So the question are these patterns specific to our colloidal roller experiments, or are they generic features of polar active matter? So to answer this question, the best thing to do is probably to forget about the microscopics of the rollers and to think about this system as a continuum medium. And that's exactly what you would do if you were to study fluid mechanics. If you want to study the flow of wine in a glass of wine, you don't want to describe the molecular interactions between water, alcohol, sugar molecules, and whatnot, right? You would rather use mass conservation. Wine is incompressible, divergence of V is 0, and momentum conservation. The mass times the acceleration equals the sum of forces. And with only two material parameters, you could describe the flows as complex as the one that is illustrated on this picture. And as it turns out, the hydrodynamics of flocking matter has been known since 1995. That's one of the earliest results, theoretical results of active matter, and it was actually put forward even before the term active matter was used. And the hydrodynamics of this type of liquid is known as Toner 2 hydrodynamics, just because it was found by John Toner and Gary 2 back in 1995. And I would like to show you this equation. Vijay, if you could just remove the blue line, it would be great. What I would like to show you is that this hydrodynamic description is actually very simple. So this is a minimalistic version of Toner 2 hydrodynamics. Specialists in the audience might be furious to see that I've omitted to write their favorite term, but this equation is really minimal. You cannot remove one of those terms and claim that you are describing a flocking fluid. So there are quite a few terms, so let me walk you quietly through this continuum description. Let's forget about the gradient terms first. So we have a non-gradient term, which is this one. And this equation is actually very simple. It describes the overdamped relaxation of a particle in the Mexican hat potential. This is our favorite Ginzburg-Landau-like term that describes the spontaneous breaking of a rotational symmetry. In other words, it means that this fluid wants to flow at a constant speed, but the direction of the flow is not prescribed. Okay, so this term describes the emergence of spontaneous flows. It does not describe the direction of the flow and the flow heterogeneities. To describe the flow heterogeneities, you of course need the gradient terms. So let's take a look at them. And these gradient terms just look like Navier-Stokes, right? This, if you forget about this prefactor, would be just your usual convective nonlinearity. This looks very much like pressure. That would be actually the pressure of an ideal gas. And this Laplacian term is nothing else but the viscous term in Navier-Stokes. So at the end of the day, the fluid mechanics of this spontaneously flowing liquid is nothing else but the hydrodynamics of a Newtonian fluid which would have to live with a soft constraint. And this constraint is to flow at a constant speed. Okay, simple. So now that we have a hydrodynamic description for our fluids, what we can do is to test whether the time evolution of these dynamics results in these bow ties, domain walls, and point singularities. So the only thing that I needed at the time was a fantastic undergrad student, and I was lucky enough to find one. So Johan Poupard joined the group and solved this equation using finite element methods. So the initial condition is just an homogeneous density and a random velocity field. And as you solve the dynamics of this equation, what you find is indeed that regions of incompatible orientations are separated by strongly localized domain walls. The domain walls form a fully connected network, and this network hosts all the point charges, all the topological defects of this vector field. And this image is mirrored by discontinuities in the density field, having the shape of the bow tie patterns I was talking about earlier. So yes, these bow ties patterns and these domain walls are generic to flocking matter. So now I would like to argue that this structure actually emanates from the -1 charges. One question was, we have one question, and the question is toner 2 valid if the surrounding fluid is not a Newtonian fluid? There is no generic answer to this question, but is certain in that. So first of all, we are studying here, the fluid that we are studying is the fluid made of the colloids only, and provided that we have velocity alignment interaction and self-propulsions, we should have toner 2. It could be complemented by other terms, more complicated terms, if you have a very fancy non-Newtonian fluid as a host fluid, but at least this part of the hydrodynamics should be preserved. Okay, so I'm getting back to the question of the origin of this. For some reason, I cannot use, okay. I'm getting back to the question of the origin of these spatio-temporal patterns. And I would like to argue that the domain walls originate from the -1 charges. And to convince you of this, we did an experiment in a channel having the shape of the figure of 8. And because of the topology of this channel having 2 holes, you can actually convince yourself that the flow should host a single -1 charge. So we clearly have 4 regions here of incompatible orientations. We have a -1 charge at the junction of these 4 regions, and they are indeed delimited by 4 domain walls that emanate from the -1 charge, as well as this density bow tie pattern, which is also centered on the -1 topological defect. Okay, and there is a question which was, okay, this is an important question actually. The question is, what is the coarse graining in particle size? So the coarse graining, so in one, okay, so one PIV box or one density box here includes more than 20 particles, okay? And the ridge is 20, thank you, Amélie. So Amélie Charda gave an answer, she actually did the experiments, 25 colloids. Okay, so Amélie in the chat, so she can answer all the questions in the chat. That's fantastic. I don't have to worry about the chat. Okay, so the -1 defects are actually dressed by domain walls. Good. How can we explain that? We can go back to our hydrodynamic description. We have all these terms. Good. So the domain walls exist in a steady state, so you can forget about the time derivative. They exist deep in the ordered phase, and you can actually check that the flow, the magnitude of the flow is constant. So this term is saturated. We also want to look at what's going on at large scale, so we can forget about higher order gradient terms. We are then left with a very simple description, right? We are just left with a description where the convective term, the convective nonlinearities, should compensate the pressure gradients. So to test whether this competition can explain the formation of the line singularities, Amélie measured the magnitude of the velocity gradients, the magnitude of the density gradients, and plotted the magnitude of this convective term as a function of the pressure term. You can see that all the data points are scattered around a line. And this line, okay, this black line is not a best fit for theoretical data. That's actually a theoretical prediction. That's just a ratio of the compressibility divided by this coefficient lambda that we can measure independently. So this agreement indicates that indeed the formation of bow ties and domain walls originates from the competition between pressure and self-advection in an active fluid. So now the question is, how can we explain that these domain walls realize a fully connected network? So to explain this, we took advantage of our numerical tool. So we initialized the simulation with only 2 defects, starting from a homogeneous density field. Very quickly, we need to observe that domain walls would grow from the core of the -1 charge. And then what we found was that the domain walls would bend and indeed connect the +1 charges. So to rationalize this observation, we can again go back to our fluid mechanic picture. And when you think about it at large scales, the Stoner 2 hydrodynamics is just the hydrodynamics of an inviscid fluid. This is Euler equation, which comes with a complication, which is that the fluid has to flow at a constant speed. But still, that's basically Euler fluid. And when you have a vortex near a wall, the rotation of the vortex is going to cause a higher pressure in this region. So we are going to have a pressure imbalance across the wall. You can think about it as a minus pressure that is going to push on the domain wall and bend it towards the +1 charge. And that's exactly what we observe in the simulations. Of course, when we get to this symmetric configuration, the pressure drop across the wall vanishes and the orientational configuration becomes stable. So this is obviously a very heuristic picture, which was actually formalized very quantitatively by Luca Giomi and his great student Ludwig Hoffmann in Leiden. Okay, good. So let me briefly recap what I've just said. That's already a lot of information. When you power the motion of particles that would undergo a flocking transition, first, collective motion emerges. So locally, the system starts flowing at constant speed. This is the emergence of collective motion. Then, domain walls form from -1 topological charges, and the pressure exactly cancels out the nonlinearities coming from the strong density gradients localized at the domain wall. So this is what happened at short time scales. But then at long time scales, we are left with very simple dynamics, right? It's basically the diffusive dynamics where D here is the analogous of our viscosity. So this is actually the dynamics that you would have in any polar broken symmetry phase, even in passive system. Okay, we just have diffusive dynamics of your Gaussian mode, if you wish, and the magnitude of your vector parameter is a constant. So given this diffusive dynamics, we expect the structure of this domain wall network and the distance between the topological defects to be self-similar. We expect all the length scales to grow at the square root of time in the system. So in other words, you expect to have an algebraic phase order in kinetics, and for instance, the number of topological defects should decay as 1/t. So the two scaling laws are obviously strictly equivalent. So to check this hypothesis, we just measure the evolution of the number of defects in the system, and indeed, it's perfectly consistent with this -1 parallel. So this is true whatever the system size, and it is also confirmed by our numerical simulations. And the cool thing with numerics is, first of all, that you can do numerics when there is a lockdown in your country, and second is that you can vary all the parameters independently and one at a time. And you can see that by varying this viscous coefficient over an order of magnitude, we always observe this algebraic scaling law and a very nice collapse of all of our data when we're scaling time by this diffusivity. So at the end of the day, the long-time coarsening dynamics is ruled by the conventional Coulomb interaction between the point charges. And this was again formalized more quantitatively by Luca Giomi and Ludwig Hoffmann. So all in all, we have a fairly simple picture that I'm going to recap again. The way flocking matter self-organizes is a three-step process. At very short times, collective motion emerges locally out of polar interactions. Then the competition between local density gradients and self-advection results in the formation of a domain wall network connecting all the topological defects. And at long time scales, the orientational elasticity or the viscosity of this active fluid results in a net attraction between charges, the topological defect of opposite charges, and eventually heal all the topological singularities of this fluid, thereby leaving a perfectly stable polar order over system spanning scales. So what I've just told you, I've just explained you how flocking matter self-organizes. So now we understand why these flocks manage to reach very smooth flow configurations. What I would like to do is now to discuss the robustness of these flows. So Cécile Claveau is asking, can we quantify these timescales? I guess you are talking about the three timescales that I'm showing here. Can I do that? So in fact, it's very difficult so the first timescale really depends on the propulsion mechanism. So there is no generic argument for that. I cannot give you a number. The second timescale really depends on the initial defect density. So it also depends a lot on your initial conditions. So the first two timescales are not universal. And for the third process, there is no timescale. That's a self-similar process. So in short, the long time coarsening dynamics is scale-free, and talking about the timescale is irrelevant because it's basically set by the system size. Thanks for the interesting question. So, okay. So now that we have waited long enough to reach this nicely ordered flow, the question is how robust is it? So how robust are flocks to disorder, which is typically the question we'd like to ask. So to answer this question, we could just study the dynamics of a herd of wildebeests in the wild. Very unfortunately, we don't have that many wildebeests wandering in the streets of Lyon. So we could not do that. And we had to get back to the lab and study the dynamics of our colloidal rollers in a microfluidic forest. So this is our microfluidic forest. What you can see, the bright and dark circles are lithographied parts. Okay, their diameter, their radius is 5 micrometers, and they are just they are uncorrelated in space. That's just a Poissonian distribution of cylindrical obstacles. So we now have an heterogeneous medium Okay, so let me highlight the location of the geometric heterogeneities, and we can fill this microfluidic forest with our favorite active particles and look at them exploring this heterogeneous environment. So that's what we see at small scales. We do see that some form of collective motion, okay, the dynamics is not completely random, but when we take a look at large scales, at what's going on at large scale, so here the diameter must be something like 3 millimeters or so, what you can see is that there is no vortex anymore. Flocking motion is suppressed at large scale. We do not have this very nice dynamics along the same average direction for all the colloids. Okay, orientational order has been suppressed at the scale of the system size. This becomes clearer when looking at the time average flow field in this geometry. So this is not a snapshot, but really the time average of the flow. So what you can see is that indeed collective motion is preserved at small scales. Collective motion occurs. You do have polar order over a finite extent, but the streamlines are clearly bent. The streamlines meander around a frozen set of topological defects, +1 and -1 defect. And I would like to call this, this phase a meander phase. So to actually investigate, to map the phase behavior of a flocking liquid in a disordered environment, we performed an experiment in the microfluidic chip where we could actually observe 32 different realizations of disorder. So in this case, this would be 30 different, they would correspond to 30 different number density for the obstacles. And so this is actually a picture of the actual device. And this is what we observed. So I'm showing you the variations of the total number of topological defects as a function of the obstacle fraction. So first of all, first main result is that for a finite fraction of obstacles in this system, we do observe perfect polar order. Okay, nearly pristine polar order. By nearly pristine, I mean that you can have smooth fluctuation, but you don't get any additional topological defect, but the one at the core of the vortex. Okay, perfect vortex, defect-free. However, further increasing the number density of obstacles, you can see that frozen defects start proliferating and their number increases monotonically with the obstacle fraction. And eventually, when the obstacle fraction becomes too large, collective motion is fully suppressed and you end up with just a gas of active particles. So thanks to this microfluidic chip, Amélie actually managed to run more than 500 different experiments. And out of these 500 experiments, we only observed 3 different behaviors. And that's the behaviors I've just talked about. We just have a gas, isotropic, no order, no collective motion when the obstacle fraction is high. At finite but small disorder, we just have this perfect flocking order, okay, this vortex state. And you have this intermediate region, which has a finite extent, in which we have this meander phase with frozen topological defects. So understanding the robustness of these polar liquids amounts to understanding the transition between this polar liquid state and this meander state. So to understand, so first of all, to talk about the transition between the two states, you will first have to establish that they are different. Cecile is asking me whether the polar liquid is always a vortex or can you have a swarm. By a swarm, I guess that you mean a compact cluster of particles exploring free space. The particles are not cohesive, so we cannot have a swarm properly in vacuum. But I can tell you that in this dashed rectangle, you have actually a coexistence between a swarm and a gas. And so yes, you can observe something different from a vortex. Depends a bit on solid geometry, and we can talk about this later. Okay, so the polar liquid is very different from the meander phase. Why? First of all, they are topologically distinct, obviously. The number of topological defects is just different. Secondly, they don't have the same symmetry. That's very clear. Here, I'm showing you the distribution, the histogram, the heat map codes for the probability of finding a flow orientation p theta PR, where p theta is the azimuthal component and PR the radial component. This distribution is peaked on the azimuthal direction. We just have a vortex. In the meander phase, the phase is clearly isotropic, right? Isotropic, polar. And the transition between these two states is very sharp. You can quantify it by measuring the orientational order parameter of this phase, namely the magnitude of the azimuthal polarization. And you can see that the magnitude of the azimuthal polarization decreases and hits zero at this critical obstacle fraction I was talking about earlier when counting the defects. I've got a question about the dynamical scaling, and I'll come back to this question later. Okay, so I've got a sharp transition between two distinct phases. And one question could be, is a meander phase just a polar liquid in which the coarsening of the topological charges would be arrested? So let me show you again these movies of showing the coarsening dynamics of a flock in an obstacle-free chamber, both eyes domain walls. So now let me show you the same dynamics in the presence of disorder in the meander phase. So clearly here, the final pattern is very different. No more both eyes. We kind of can distinguish some domain walls, but they clearly do not form a fully connected network. So the shape of these meander patterns cannot be explained by a mere arrested coarsening. So how can we explain that? So I would like to convince you in the remaining of my talk that these meanders realize the analogous of a dynamical vortex glass. So to convince you, let me show you the flow field measured in two experiments corresponding to the same realization of disorder. This is experiment alpha, this is experiment beta. Even though the location of the obstacles are identical, you can clearly see that the two flow fields are very different. And the location of the topological defects of the vortices are not the same. So the position of the defects are not deterministically set by the realization of our geometrical disorder. So to quantify the difference between these two experiments, we can use a tool that is very common in disordered system physics, which is the overlap between these two replicas. And this is nothing else in our case but the scalar product between the local orientation of the two flow fields in the experiments alpha and then the experiment beta. So to give you a bit of intuition about this, what this overlap field quantifies, let me first show you the overlap between two experiments in a pure case and an obstacle-free chamber where the two vortices would actually have the same handedness. The overlap would be 1 everywhere, but in the core region. Good. If one vortex rotates counterclockwise in experiment alpha and the second vortex in experiment beta rotates in the clockwise direction, the overlap value would be very close to -1, but in the vicinity of the vortex cores. Good. So now what happens when you add disorder? When you add disorder in this meander phase, what is very clear is that the two flow fields are associated to an overlap map, which is very heterogeneous, right? And what is really remarkable is that if you look at the value of the local, at the local overlap value, this value is either +1 or -1. So this is the histogram of the values of the overlap. -1, +1, strongly peaked. What does this mean? This means that in two different replicas, the flows are either equal or opposite, either parallel or antiparallel. Okay. Good. So disorder induces some channeling, and in these effective channels, the fluid can flow either in one direction or the other. And what is also quite remarkable is that the shape of the obstacle, and I might have not said that, but the shape of the obstacle is just isotropic. So we just have isotropic and homogeneous disorder, and yet you see that this distribution is asymmetric, meaning that isotropic and homogeneous disorder is capable of polarizing the flows of this active fluid in biasing the direction of the flow, even though there is no intrinsic bias in the shape of the obstacles and in their spatial distribution. So, okay, Amélie showed me that two different experiments could result in two different patterns. So I asked her, okay, so how many different patterns can you observe? And so Amélie repeated the experiment more than 50 times, and she compared more than 1,000 of different pairs. And we never observed two identical patterns, never. So the natural question now is, how many patterns, how many different patterns do we have, right? It's difficult to give you an accurate number, but you can actually try to estimate the number of different meander patterns that you can have in your experiment. To do so, you can measure the correlation length of this overlap field. And this correlation length is basically a measure of the regions where the flow is unbiased. So you can measure the decay of the correlation function. You can see, first of all, that it decays exponentially, so you can define clearly without ambiguity the correlation length for the replica average flow. And then you can, so it's about 100 microns here. And then you can remember, and you can actually see on this map, that you only have two possible values for the direction of the flow. Okay, I have a +1 or -1. Meaning that the number of distinct flow patterns goes as 2 to the n, when n is a number of regions where the flow is not biased by the obstacles. And this n is nothing else but the ratio of the system size by the correlation length. So in other words, what I'm saying is that the number of distinct flow patterns grows exponentially with the system size. And this is a hint that this meander phase might indeed realize a dynamical vortex class with an extensive complexity. So John is asking whether in the replicas the disorder is the same, and the answer is yes. Only the initial condition changes.
Wait, what do you mean initial condition?
We inject the colloids in the channel, run an experiment, randomize the position of the colloids, motorize the colloids again, etc. So the initial condition is basically the spatial distribution of the colloids at rest.
But the obstacles are at exactly the same positions.
That's actually the same device.
Okay, yeah, okay.
Okay. Okay. And I answered the technical question about the randomization and the question about ventilator. Okay, so how can you actually further ascertain that this topological charge distribution might realize a vortex class? You can go back to your favorite continuum theory. Okay, so this is number 2, convective nonlinearities, pressure, elasticity or velocity, depending on how you want to think about it, and your symmetry breaking term, your spontaneous flow term. Now you want to account for the presence of spatial heterogeneities. You want to account for the presence of the obstacles. The obstacles are isotropic. So the only characteristic of this obstacle distribution, which is a Poissonian distribution, is just the obstacle number density, the obstacle fraction. And the only vector field that you can construct out of the number density is a gradient of this number density. So from purely phenomenological consideration, from symmetry considerations, this order must alter the regular Turner-2 picture as a random in this form, which is nothing else but a random pressure term. Okay, so to test this, you can look at the linear response of this system to this random perturbation. So you do a spin wave approximation, you can compute the value of the order parameter, and you can see that this black line is a prediction. And it tells you that the order parameter should decrease linearly the obstacle fraction, and that's exactly what we observe. So we use one fitting parameter that is the value of this repulsive coefficient, and as it turns out, we can also estimate it from the microscopics, and the agreement is just perfect. Okay, good. So we are confident that we have the right picture to account for the impact of disorder on the active flows. But what we want to understand now is the formation of topological charges. That's by definition something that you cannot capture by a spin wave approximation. So you can simplify your problem. Okay, so we are deep in the ordered phase, so let's forget about this term. Let's just say that the velocity is a constant magnitude. The vortices exist in steady state. Let's forget about the time derivative. Let's take a look at the system at large scales. Let's forget about elasticity. Let's also focus on the strongly disordered limit where beta naught or phi naught are very large. So you could even forget about the pressure. And you are left again with a competition between convection and pressure. But in this case, the pressure originates from the obstacle distribution. And the last thing that you need to do is to go to an actual conference and drink a coffee with Suraj Shankar and Christina Marchetti. And this proved to be an very effective way of solving this problem. To solve this problem, and I'm going to make a very long story short, you can start by Turner-2 hydrodynamics, including the disorder term. And given the simplification that I've just showed you, you can actually map the steady state of the flow to the ground state of a random gauge XY model. Okay, using only the competition between disorder, random pressure, and convection. And once you have established this connection to random gauge XY model, you can heuristically study the Gaussian fluctuations of the orientation around this background disorder. And what you can show is that indeed, using a Kosterlitz-Thouless type of argument, is that indeed you need a finite obstacle fraction to nucleate topological defects. And this fraction, and this is now not surprising, is determined by the ratio between the magnitude of the convective nonlinearity and the magnitude of this beta naught term that controls the random pressure. So together with the observation of this extensive number of Meander configurations, the mapping to this random XY model gives us more confidence when claiming that this Meander phase is akin to a dynamical vortex glass. And that's the formation of this glass phase that actually kills the long the steady and pristine flows of flocking matter. So this was a lot of results that I wanted to share with you today. So this is the last one I wanted to talk about. So before answering the question that have been asked in the chat, I would like to thank again Luca, Ludwig, Johan, Suraj, and Christina, who contributed to the theory and the experiments. There are much more theoretical work than the one that I've showed today. And I've already mentioned the fact that all the experiments have been performed by a truly outstanding student, Amélie Chardac, who is about to leave Lyon and to join Guillaume Duclos' group in Brandeis. And with this, I guess I should thank you for your attention and tell you that I would be happy to take any question. So thanks.
Thank you, Denis. I just have a suggestion for people who have questions. You can raise your virtual hand so I know which order to call upon you. But going back, there are a few questions in the chat. Denis, should we tackle those first?
Okay, so let me share the screen again. Okay, so chat. Okay, so Ben asked a question about this number, I guess, and that's indeed an upper bound because the distribution is not symmetric. That's a very good point, and this would result only in a factor of 2 in the exponent. So this does not change the exponential form. How do you randomize the position of the colloids at rest? We just inject more colloids, or we can use a regime where at very high field intensity, and it has been beautifully explained in a recent paper in PRL by others, that there is a regime where the colloids freeze their, not freeze, but oscillate around a fixed position and stop running. So you can actually freeze the dynamic of the colloids, let them oscillate, and then you stop at some point, and the results of these uncoordinated oscillations randomize the position of the colloids. So you can either inject a fresh solution or just randomize the positions like that. Angular momentum in the system in its time evolution or density dependence. So I don't exactly know what you mean by that. So first of all, neither linear nor angular momentum is conserved in this system. And an important point is that here I've been referring to, and there's another important point, is that in this system, the orientation of the particles is slaved to the direction of their motion. So the direction of the velocity is a direct indicator of the orientation of the particles. So a comment by Tom, wow, that was so great. Tom, I cannot agree more with you. Cecile asked, as I had a question about the figure of 8 being asymmetrical.
Cecile, maybe you can clarify.
Okay, the figure of 8. So where?
No, I didn't mean, yeah, not figure number 8, but this 8.
This one, yeah, this one is asymmetrical. You can make it symmetrical. It doesn't matter at all. The only thing that matters is really what's going on here at the junction between the 4 domain walls. It was just to make the picture pretty and look actually like the actual figure of 8.
Okay, thank you.
Narayanan Menon saying, great talk, thanks. I mean, I cannot agree more. Okay. Good.
There was a much earlier question about the difference between motility-induced phase transition behavior and the repulsive active particles, in repulsive active particles and in the behavior you've shown us in the flocking transition. Is it mainly the polar interaction that differentiates the two?
Absolutely. So motility-induced phase separation is just a completely different situation. To get motility-induced phase separation, the only thing that you need is just a conserved number of particles, and you need the particle current to decrease with the particle density. Okay, and then you get phase separation. It has been beautifully studied by a number of groups, and I think we can say that it has been fully understood. It's now fully understood. As it turns out, in this system, you can observe motility-induced phase separation when the density is very high. Okay, a traffic jam can happen in the flock, and you can also observe motility-induced phase separation, but at very high densities. The flocking transition is something that is completely different, and that really relies on this existence of a polar degree of freedom that is coupled via these polar interactions. And flocking is really a spontaneous symmetry breaking, the emergence of polar order, and that's not something that you have in motility-induced phase separation. They are just completely different. It's a bit like asking, is the liquid gas or liquid oil phase separation the same thing as the emergence of nematic order in a liquid crystal? They are just two separate problems.
Mm-hmm. John?
Yeah, I was wondering, I mean, I know experimentally this would have to be, I guess, a completely different system, but have you thought about 3 dimensions and how these defects and things and scaling laws would change?
So as far as I know, no experiments have been done in 3-dimensional active matter having this type of behavior. There is a recent paper in Zvonimir Dodgik's group where they studied precisely the dynamics of topological defects in active nematics. They know how to make absolutely beautiful 3D active nematics, fully synthetic. But in our experiment, the motility is based on rolling motion. You need a substrate.
Yeah. But in a simulation, you could, I guess.
In simulation, sure. As far as I know, the only study about, quantitative study about the coarsening dynamics has only been done in 2D, even numerically. But there is no limitation. I mean, this is a well-posed problem. You could study the coarsening dynamics in 3D, but I would not know what type of experiment you could compare it to.
There was a question from Jonas or Jonas Denk. Do you want to ask yourself? No?
Yeah, hi. I was just wondering, sorry, my video is not working at the moment. I was just wondering if you, looking at these colloids, if you've tried out or played around with different materials or coating of the colloids to change the interactions, or even maybe make them a little bit asymmetric to change the dynamics.
Yeah. So we are currently investigating this type of question. I can tell you that for homogeneous and spherical particles, you can basically use whatever colloid you want: silica, polystyrene, PMMA, TPM, and they all behave the same way. We also had fun using colloids that were synthesized by in the group of Stefano Sakana at NYU, and the colloids are silica beads and have a magnetic core. Okay, so in addition to the interactions that have been alluded to today, you also have magnetic interaction between the particles, and this drastically changes the collective behavior. So we don't have this was a side project. We don't have I don't have quantitative results to share with you today, but I can tell you that the phase behavior is drastically different. So there are plenty of room to explore with this system.
Jack, you had a question you want to ask yourself?
Sure thing. I hope you can hear me. Hi, that was fantastic. You showed this video the active pneumatic right at the beginning, where there's some kind of typical defect spacing and you have this turbulent state. So is there an easy way to understand like why the defect dynamics is so different here? Why everything coarsens to the system size as opposed to having that, you know, that active pneumatic length scale, say, you know, contrasting the two?
Okay. So the thing is that I don't want to make, I mean, the active pneumatic case, now it's clear. In 2D, the reason why you have continuous proliferation, the instability, like the interplay between flows and deformations and active stresses, all this is like under control in 2D. I'm not going to comment on that. In this case, let me share my screen and get back to my slides. Yeah. Where is it? That's this one. Okay, so let me try to recap again. In this system, at short time scales, the system is just set in motion. Polar order emerges locally. Okay, this is the result of the microscopic polar interactions. There is something really magic that happens in this flux, which is that you have very complex, like fairly complex hydrodynamics, and yet pressure and self-advection, for some reason that we don't explain, that's just an experimental facts, they just cancel out. And the way they do that is by growing domain walls out of -1 topological charges. But once these two terms are balanced, you are left with, where is it? Sorry. You are left with a very simple dynamic. So this one, sorry, and show you here. Okay, you are left with a very simple situation where you have topological defects living on a fully connected network, but this network does not have a funny geometry. Okay, it's fairly irregular. And you have this term, this elastic term, and you know that in 2D, this thing is going to yield, the spin waves are going to mediate elastic interactions between the colloids. Okay, and this has been worked out quantitatively by Luca and Ludwig. So once you know that you are left with diffusive dynamics, okay, you know that the fate of topological defects is to annihilate by pair. There is no other choice. The magic is this cancellation. Okay?
Thank you.
Devasmita, you had a question. Do you want to ask yourself?
So is it?
Yeah, hi.
Yeah.
Thanks for the great talk. I had a very nice question. Like, if you have a disorder which is in the form of concentric rings around the middle of the chamber, but you have gaps in between them.
So could you repeat it again, please?
Yeah. So if you have a disorder, like which you design in such a way that they're in concentric rings around the midpoint of the chamber. And
I don't understand. Can you draw? Can you sketch the geometry you have in mind?
Let me see if I can.
I think if I may interpret, she means if you have your circular geometry and then rather than have your disorder in those lines, you put them in concentric circles around the center.
Okay.
With gaps in between them and such that you allow folding, like those strain fields to form around different radii. Will you get a final state in which you see the vortex fluid?
Okay, so if you, okay. So we haven't done the experiment, so I can not answer for sure, but what I can tell you that, let's say that if you have a radial gradient of obstacles in a chamber, you could explore the full phase diagram, okay, regardless of whether the gradient is inward or outward. Okay, if you cut the geometry of the chamber is really unimportant. What really controls the the destruction of polar order is the local obstacle density. Okay, by local, of course, at a sufficiently large scale, but small compared to the system size.
Okay, thank you.
Cecile had another question about Quinker swimmers. Cecile, you want to ask?
It wasn't so much a question as someone was asking about 3D Quinky particles. And I just wanted to point out there's been a very recent paper with Quinky swimmers where they have little
yeah, you can actually bind flagellas to a bead,
yeah.
use a Quinky rotation, this creates the beating motion of the bead, and these things swim. As far as I remember, they are not quite 3D. They do not swim freely in 3D, and given the system size and the way they are actually engineered, it would be difficult to envision making a bucket of these particles. But this exists. And look, there are other ways of motorizing colloids, and I hope that we will find new ones in the near future. So they don't have to be Quinky.
Yeah, okay, sorry, I sort of thought it was 3D, but I wasn't sure and I didn't even remember the name of the paper. So it was just...
The paper the work has been done in Howard Stone's group. I think it has been published recently in PRX. Okay.
Denis, can I ask a question as well?
Sure.
So the dynamical vortex class that you're showing, is that system something that we should expect to see like in the cell or in biology or in somewhere? Like, does
So I'm
it
going to be
occur
super cautious here because first of all, we only have observations in polar systems. Okay. And the analogy works by definition for polar systems. My intuition is that you could have the same thing in active nematics. Okay, but you would need the typical distance between the frozen defect to be smaller than the nematic correlation length, otherwise this would not mean much. Okay, I don't know whether this could be relevant to an actual biological system, but at least I could say that I would expect a similar phenomenology to occur in active nematics, in base or active crystals actually.
Mm. Yeah, because I mean, in real systems, you would expect like,
yeah,
you know, there are obstacles, there's stuff, right? Like
there is stuff, absolutely,
yeah.
absolutely.
But I think that's really
the question is, what's the coupling between the active medium and this stuff? Okay, and as it turns out, which changes a lot the phase behavior. So there is recent literature on the top on the impact of disorder on flocking motion. So depending on whether your obstacles repel the active agents or whether they align the active agents or they apply torque to the active agents, the phase behavior is just completely different. Okay, so this is fragile. Okay, the least that you can expect is to have steric repulsion. So I believe that this ingredient, okay, should be fairly robust. But if you add more to it, you can really mess up with the phase behavior.
Thanks. Yeah, super interesting.
So maybe, is there a new message? There is a question from Vishnu Krishnan. Do you want to ask, Vishnu?
Yes. So you showed lots of replica pictures, and some of them did not have singularities in locations where other replicas had singularities.
Yes.
So how are the flow fields ignoring some of the obstacles? I mean, obviously there are obstacles there because there happen to be.
I understand your question. So I might have I might have been unclear. So let me show you. Yeah, the two replicas. Okay. Sorry. Here we go. So for instance, this bunch of defects, you cannot find it here, right?
Yes.
So what you have to keep in mind is that this is a coarse-grained picture. Okay. So for instance, this arrow here, this velocity, okay, corresponds to the instantaneous speed of the rollers average over a finite region of space. Okay. So in one bidding window, you have something like 20 different obstacles. So it's not like one obstacle arrests the motion of the flow. Okay. The obstacles only change the path. Okay. Change the shape of the streamline. Okay. And you have many ways of, like, let's say that you have a high density of obstacles here. And let me stop showing my screen. I need to express myself using my body. Okay, so let's say that you have an obstacle here, you have this flow coming here. Okay, so you can avoid the obstacle going like this or like that. Okay, so you have two options. Now imagine that you have a collection of obstacles. Okay, so the number of different choices is going to grow like crazy if the system size increases. And that's basically what we see in this experiment. Okay, you might have a bunch of obstacles in this region here, but they are not dense, concentrated enough to suppress collective motion or to change the orientation of the flow. But when you hit a region where the density is sufficiently large, okay, when the density gradient actually is sufficiently large, then the flow is going to be, the flow direction is going to be altered, and the number of these possible choices grows exponentially.
Okay, thanks.
Denis, maybe we should end with a question from Tom, who's left, but he said, what's next, Denis? What's the biggest unsolved puzzle?
Okay, I've got a very clear answer to that question. Cure COVID swiftly so that we can meet in an actual conference room.
Yes, yes.
Okay, and okay, I'm not going to do that, unfortunately. So I guess that in active matter, now we have this bifurcation point. We can use all these tools and concepts either to explain what we see in nature or to propose new design rules for a next generation of materials. Okay. And there are very interesting avenues in the two directions. I'm currently very much interested in trying to apply these concepts to actual flocks, schools, herds in the wild. And the number of available experiments is very scarce. So I would say that on this axis, we need to do experiments. And I think a better quantitative understanding of animal or human crowd behavior could be extremely useful to regulate migration, to preserve some species, of course, in the case of crowd, to guarantee safety, etc. So there are actual applications, but there are also some very fundamental questions, especially because in nature, it's very rare to observe groups of millions of individuals. And we are always dealing with finite size effects where these very nice hydrodynamic descriptions start breaking down. And there are some beautiful early results along this line that have been published by the Giardina and Cavagna group in Rome. But there is also much more to do to understand actually the relevance of these pictures to actual animal groups. On the experimental front in active matter, I would say that there is definitely a need now to move from the laboratory experiment to actual materials and to connect fundamental experimental physics to material science. There is a gap that has not been, this gap has to be closed very swiftly, otherwise it's going to end up being just a game that we enjoy playing in the lab. But I guess we have to work hand in hand with chemists and material scientists to to move to the next level. Okay.
Okay, thank you very much.
Thank you.
Thanks a lot. Thank you very much.
Everyone. Denis, thank you so much.